This works a little better for me as I'm not feeling like an elephant with the trunk down in front of my nose. So, welcome back to Marshall Land. Last iteration of this school year. So that's a good thing. We got people graduating in here, at least one I know of. So, yeah, it's been a long journey, hasn't it? Yeah. Okay, got a couple things for you tonight. You're first going to have to put up with my closing arguments, ear banging, try to summarize what I think is important out of this whole experience for the year, and then we're going to take an adventure into MIG welding, and you're going to do the welding. Ooh. Yeah, that'll be fun. Throwing some sparks and hot metal around. Woo! Did you ever think? Okay, well, we're going to do a little bit of that tonight. Yeah. So we went through and another, this is year 10, I think. Yeah, this is year 10 of Northwest Nuclear Laboratories, known as Northwest Nuclear Consortium. I don't think we had any other names in this location. It was known in the dim past as KJNW, but no one remembers that. So the program has been about science for 10 years. And one of the questions, I don't know if it ever occurred to you or whatever, is, wait a minute, this guy isn't charging money for this. Why is he doing it? Why is he doing it in his basement? What is he doing this for? Like, come on, this is a lot of extra work, and a guy spending some money and doing all of this science stuff, and why isn't he doing what other Microsofties do, right? And wherever that is. Well, maybe we'll visit that a little bit, because it kind of comes into the realm of what's important. But we're going to start off with the question, and I've asked it before: what is science? Science class, right? So, are we clear after a whole year of this about what science really is? Because you're about to, those of you who are graduating, go off to an institution called a university, and there you're going to meet all kinds of professors who are going to try to indoctrinate you in their perspective of science. But there is some fundamental cornerstone data point that you dare not let go of, because there's a strong wind blowing and it'll blow you away when you get to college and you don't have these things nailed. We're going to touch on them again tonight. Okay, so science is a methodology of questioning nature built on truth and logic. Ooh. There's that truth word again. That's controversial. Is that politically correct? Truth. Well, in all truth is simply that understanding which corresponds to reality. So, if I have truth, then it's real. Ta-da! Boy, that sounds hard, doesn't it? So, reality is something that is separate from our perspectives. And the closer we get in our perspective to what is real, the more truth we have. So that's important. Truth is not popular opinion. Truth is not even accepted opinion. Truth is totally predicated on its correlation, its correspondence to reality. That's the only criteria. Period. Okay? Logic, because we said truth and logic, logic is the process of demonstrating that correspondence. So, I can, through logic, demonstrate that 2 plus 2 equals 4. That's the purpose of logic, to make sense out of and to illustrate the correspondence to reality of a given truth. You say, well, hey, Carl, you're getting pretty granular there. Is there a real need to drive it to that level? Oh, yes, there is. Because these are the cornerstones that people are playing with and trying to get their fingers under and change the meaning of. Don't let go of them. The scientific method consists of the following points. Science is predicated on empirical truth. In other words, things that actually exist. And things that are testable. Things that are falsifiable. And ultimately things that can be peer-reviewed and duplicated reliably and repeatably. Science has to do not just with a good idea. That doesn't make science. Science has to do with the business of conducting an experiment to prove there's a correlation between certain inputs and an output. And that correlation or law or principle is repeatable, connected to reality. Anything that does not meet these criteria is not scientific theory or fact. And there's a whole lot of things that are being floated by scientists today, well-known, reputable scientists, which don't meet this bar. I'll be polite, I'll listen, I'll nod, I'll smile. I don't agree, and I'm not buying it yet. Because it's not empirical truth, it's not testable, it's not falsifiable, and it hasn't been peer-reviewed. It's just popular. Be careful. If you want to be a scientist, understand that science is done with rigor. Science locks down limitations on conclusions. Now, something else that we study around here. Cosmology. What is cosmology, or the cosmos, or the universe. Got a bunch of words for it. Our universe has intrinsic regularity. What did he say? Intrinsic regularity. Mathematics is a corollary to that regularity in the universe. Now, mathematics is this really cool bunch of symbols that have relationships and can be manipulated with tremendous precision to correspond and illustrate the behavior of things in our universe. And this correlation is so precise that it can actually predict things in our universe before it happens, before they happen. We can predict solar eclipses. Why? Because we understand the math. We know gravitation, we know orbits, we know the movement of the bodies in the solar system, and we've mapped it all out, and we can send rockets and they arrive at their destinations. So mathematics is a corollary to the regularity in the universe, but it's more than that. Mathematics talks to us about intrinsic values in the universe and things that, frankly, like imaginary numbers, other dimensions, things that mathematics suggests that we don't experience in our universe. Or do we? According to mathematics, our universe is about 95% dark matter and dark energy. We'll come back to that. This regularity in our universe is unique in that it is fine-tuned and statistically improbable. Not impossible. No, it's totally mathematically possible. Absolutely mathematically possible. And utterly, completely preposterous. Statistically, mathematically preposterous. And you're insane if you believe that it would ever happen. For instance, the chance that the universe would have the entropy that it does is one chance in 300 billion raised to the 123rd power. Try to get your head around that number. 300 billion raised to the 123rd power. That's why I say it's preposterous. And oh yeah, there's 67 other constants equally as fine-tuned things like the mass of the proton, the mass of the electron, the mass of the neutron, strong nuclear force, weak nuclear force, gravity. We can go on and on and on, and they are all within about 2% of each other, and if they were off by any more than that, the entire universe wouldn't exist. And the fact that these all line up so succinctly to give us stars and galaxies and planets and minerals and elements and chemistry and the properties in chemistry is so improbable as to be utterly preposterous. That's what mathematics tells us. Mathematics reveals principle, precision, consistency, and correlation. Principle, precision, consistency, and correlation. Between entities from chemistry all the way out to nuclear physics. Mathematics is impervious to culture, religion, skepticism, or politics. In other words, 2 + 2 = 4. I don't care where you want to take that. It doesn't change. You're never going to say it any differently without sounding like a complete idiot. Mathematics is telling us that 95% of the universe is unseen. Why is that? Well, there's a whole lot more mass in the universe than we can see, and we can tell that because we can look at the way gravity behaves. And the stars at the edge of the galaxy should have been flung off into space at the rate that the galaxies turn, and they're not. And that shouldn't happen. And we have the math to prove it. And it doesn't make sense unless there's a whole bunch of stuff out there that we can't see. Okay. Oh, and there's another problem. The universe is expanding. Oh, and it's accelerating while it's expanding. Oh, wait a minute. When something goes bang, there's an initial force that throws it outward. And from that moment on, that stuff that's flying outward decelerates. It doesn't accelerate. But that's not true of the universe. We have come to learn through the redshift and some very precise measurements that not only are the galaxies receding, they are accelerating in the process of that recession. Something we can't see is pushing on them. Okay. But you see, that's counterintuitive, because if all the mass came from one place, that's where the gravity is, and therefore gravity should be trying to pull it all back together again, or at least slowing it down so that at some point it would fall back. But no, this is accelerating outwards, and it defines a point in time when the universe will never collapse back on itself. So we have a universe, and we also have an infinite endpoint called heat death, when everything gets so far away from everything else that there's no longer any interaction. But we also have this tremendous amount of power that we can't see and this tremendous amount of stuff that we can't see, and we're only 5% or less of that stuff. Let me throw a thought at you. Could all that stuff and all that power be two properties of the same entity? Why not? We don't know what it is. It's more logical to assume that if we've got a whole bunch of stuff out there and it is also generating a whole lot of power, that we could answer two questions at the same time. We'll touch on one more thing, that there is an immense amount of, like that mass and like that energy, there's a third thing out there, and all that we brought to the table is only 5% compared to the total that we find in our universe. I'll be back to that in a moment. Mathematics teaches us that the universe had a beginning. We've only got 14.5 billion years to deal with. And that actually, when you're talking about infinity, is kind of a blip on the time scale. It's a very interesting blip. But bottom line, we can, with mathematics, chart the trajectory of the stars, and we figure out that there was a point in time when all this was in a pickle jar somewhere. Interesting thought. Mathematics demonstrates the non-random aspects of that beginning. And that ties us right back to that 300 billion to the 123rd power. That's no random accident. Any more than gravity being off by 0.5% would cause the universe to either collapse or explode so quickly that no proton would ever get a chance to form anything more than just diffuse hydrogen. We would have had a lot of hydrogen gas just kind of going off into the black. That's it. Okay, so finally, the other subject we covered in depth, biology. What is biology? We now understand that at bottom, all of biology is mathematically driven by the uniform information processing of software called DNA in the nucleus of a cell. Oh my gosh. And that we are full of machines. Hard, cold, well, actually 98.6 degrees. Machines that are doing stuff inside of our cells. Predictable, reliable, and they operate according to scientific principle in mathematics. And we've been into that DNA far enough to understand that there's a whole bunch of connecting switches and controls that have to do with disease and heredity and personality and all kinds of things we didn't know were there. Appropriating the genius of biological systems is called biomimetics. How many of you have ever heard of biomimetics? Biomimetics, or biomimicry, anticipates the value in the advanced design we see in nature and appropriates it to human technologies. You can go study this at the university. You can get a career in it. It's reverse engineering nature and building high tech out of it. Ooh, such a deal. Nature teaching us science? You bet. As an outcome, future biological research is moving towards software simulation to establish outcomes for new pharmaceuticals, therapy, and vaccines. In short, the laboratory is quickly moving into the computer room. As we get more and more understanding around how to turn genes on and how to turn genes off and gene regulatory systems, we're discovering it's all software. And once we have the code, we can take that software, put it in a computer, and figure out what we need to know. It's just a computational problem at that point. Further, the information enigma demonstrates the non-random design of cellular life. Anyone here know what the information enigma is? We've talked about it. It's been on movies that I've shown you. It's this. Where did 3.5 billion letters of code come from in the DNA? Well, only 2% of that is any good. That's the encoding the proteins. The rest of it's junk DNA over the thousands of millenniums of evolution, and that's not true. The ENCODE project in 2013 to 2017 went in and did an analysis of the non-coding areas of the human genome and determined that 85% on first pass of the non-coding areas of the human genome are regulatory gene process and vital to the operation of the cell and the differentiation of cells and the construction of a human body. And the whole junk DNA theory went right in the trash can. Oh, but you can hang on for a moment and have some solace. There is out there a thing called rationalwiki.org, and you can go out there and read absolute ignorance stated by people in denial who are still trying to bang the drum around the non-coding regions of DNA and tell us it's junk, even after scientists at the University of Washington are publishing consistent information on almost a daily basis about the gene networks and how regulatory networks turn genes on and turn genes off and control disease and everything else. All this stuff is now accepted across the industry, and there are literally thousands of labs mining this junk DNA for its value. But the naturalists said, oh, don't go look, don't, they're wasting money. It's stupid people go look. You don't want to go look, because if you find something, that would mean we're wrong. See how that works? Yeah. Evolution explains the survival, but not the arrival of the species. There is clear and obvious evidence that life adapts to its environment. And some of that adaptation is genetic. However, there is no clear evidence of one species becoming another species. There is no connecting link across that boundary. It doesn't exist. In fact, the Precambrian boundary clearly shows us something else. At 570 million years back, we have 90% of all the body plans all at one time that come up within literally a blink of archaeological time. And we can dig down just a few centimeters beneath that layer in the sediment, and we come up with the embryos, fossilized embryos of sponges. Nothing more complex than that. Well, what does that tell us? Well, first of all, it tells us that the emergence of these body plans were not just the emergence of skeletal structures that would survive fossilization, because embryos are not skeletal structures. They're soft-bodied tissues, and they're there a few centimeters down, and they're fossilized. So what that means is, if there had been something there, complex and a precursor to the existence of these other life forms that now exist as the primary body plans, we would have found the evidence for those. But they don't. They just don't exist. Okay, so why does this matter? Why is it so important that a computer scientist from Microsoft had to go make a science school in his basement and put in a bunch of laboratories because he didn't like what was being taught in school, because he felt that the truth wasn't getting out? And why does it matter? Why should you care? Well, there's the story of junk DNA. Stop and think about it. We're scientists, right? The whole job is to go out and find new scientific discovery, right? And yet, a bunch of people got so upset with the idea that junk DNA might not be junk that they fought with all their might to stop the research and punish the scientists who were doing it, and cut off the funding. And had they been successful, we would never have the whole story of gene expression in front of us. A whole area of disease and possible medicine would have vanished from the earth. Retaliation against scientists of dissent. Is it happening? Yeah, I've got 3 books right here. These are Censoring the Darwin Skeptics, Slaughter of the Dissidents. These are case histories in 3 volumes of men who've lost their careers, lost their incomes, lost their reputations. They've been maligned and destroyed and whited out of history books because they dared challenge standing theory. Oh, nice. Anyone who persecutes you for your scientific opinion is a bigot. Because in science, the objective is we go looking for things, and if we find them, hoorah, and if we don't, we keep looking. You're not bad if you don't find something. Suppression of opposing opinion thwarts objective research. Microsoft knows this, and we allow a tremendous diversity of opinion in all of our labs, regardless of whether or not we feel the opinion makes sense or not, because that diversity promotes ideas that surprise us, that delight us, that ultimately lead to new products and innovation. The story of nuclear technology in this country is a sad story. We had a corner on nuclear power, and we were producing a great deal of it. But now our reactors are closing down one after another, and there are no new ones coming online. You know why? Because reactors aren't safe. Wait a minute. Were airplanes safe when we started flying them? Do you know how many airplanes have fallen out of the sky full of people who did not get up and walk away? Did we quit flying because of that? Of course not. The industry went to work, made better airplanes, implemented safety programs, and it got so that flying airplanes was safer than driving cars. And statistically, that's true today. There's no reason that nuclear technology couldn't follow the same course. Look at what's happened with rockets. We blew some people up, but now rockets are getting safer and more reliable. And we're starting to do more space exploration. We've got better rockets. They're doing more reliable things. Why are we getting rid of nuclear power at a time when we desperately need a carbon-free solution? Because oil and gas is profitable. That's why. Makes big money. The environment is on the chopping block. And stuff that's getting presented as science changes from presidential administration to presidential administration. Have you noticed that? That's crazy. Now we have alternative facts. Alternative facts? Science is a search for truth. And we accept something as true because it corresponds to reality. But we're being offered something new. Accept this as reality because I'm popular. That's so sad. Do you know what happens when you try to do science on that kind of logic? Will you ever find anything? Within popular dogma, there can be no true discovery. That is the bottom line. Within popular dogma, there can be no true discovery because what is true is dictated by who's in authority, not by reality. That's the choice that's in front of you tonight. That's why this school exists. That's why I'm here to teach you to think so that you can look at what you know to be true and defend it and hang on to it against all odds. And it should pass scientific, investigation. It should be tested with rigor. You should hold it to the test to make sure that what you believe is what you honestly in your heart know is true. But without that degree of honesty inside of ourselves, I don't believe we can do true science. And I don't think we can be true scientists. I think we are just simply paid nameplates that are holding things up that government wants us to and buying off on them. Anyone know who the FDA is? Food and Drug Administration? Yesterday, they released and okayed an Alzheimer drug that the 11 scientists who were internally charged with the investigation by the FDA had said, this stuff is bogus, it doesn't work. One guy said he wasn't sure. The other 10 said, it's bogus, it doesn't work. Nobody said, hey, this is great, it works. Not one single scientist. And the FDA came out and said, we're going to go ahead and release this, and you can start prescribing it. What's wrong with this picture? Three of those scientists have now quit, summarily walked off the job. That's courage. That's the kind of courage it takes to stand up and look the system in the face and say, I'm going to expose this. And so tonight on CNN, there were all kinds of interviews with these scientists who were saying, no way does this drug do anybody any good. But you can go buy it at the store. How sad. And we taxpayers pay these people to protect us. Why? Science is more than glassware and test tubes. And I know that when you came here, you wanted to play in the laboratories. You wanted to put on that vesture of science and the prestige that comes with it for being a person of integrity and honesty who finds great and new wonderful things that humanity can appropriate for quality of life reasons. Some of you will. But along the way, there are going to be those who try to subvert your good name for unprincipled gain. Don't let them do it. Be true to yourself and your science at any cost. You may be holding the world in your hand. You don't know. Depending upon the severity of the impact of biology, one bad mistake with the gene pool in our species won't exist in 2 generations. Boom. That's the kind of stuff we're playing with. We release something to the general public that they think is okay, and 2 generations later, there's no more babies born. Then what? Boom! Humanity vanishes. Yeah. It's a serious time to be a scientist. And I believe the most serious part of science is ethics. And I want you to understand why. There's a cost. You have to live with yourself afterwards. Thank you. I've enjoyed the time with you. We're going to go do some welding. So we're going to change this environment, and we're going to go out in the garage, and actually we're going to do something else first. We're going to visit the welding machine.
Carl?
Yeah.
May I add a footnote for you?
Please do.
Can anyone tell me what the definition of a species is? Okay, well, we define a species as 2 different species cannot interbreed and produce viable offspring. That's the basic definition for a species. If you mix a lion with a tiger, depending on which is the male, which is the female, you get a liger or a tyon. And those cannot then give birth to anything else. Well, we've got a brand new problem, and it's called the Pizzly bear. The polar bear mates with a grizzly bear and produces an offspring called a Pizzly bear. And that would have to be sterile. But now we've had a Pizzly bear mate with a grizzly bear and produce offspring. So now science has got to figure out a brand new definition for species. It just doesn't fit anymore.
I wouldn't want to tangle with one of those.
No. Let's take 2 of the meanest bears and cross them, yes.
Oh, yeah, that's right up there with breeding tarantulas and pythons to see if we can get an 8-legged python. Yeah, that's a good idea.
No, they're doing this in nature. This is not man-made.
Okay. This is the welding cart that we cooked up, or actually started last week. Here it is now, all complete. We're going to visit some of its components. Let me see if I can get another camera to look at this. Is that? Yeah, that one. Okay. We will change things around here. did I borrow the camera? I did. Okay, that camera won't work. So, we'll cut back here. Do things the hard way. Okay, well, I'll come down here and we'll go through this at camera height and talk about the various features on our welding cart and what's here and what it's for, so when we go out to use it, you've kind of got an idea of what's going to happen. So, this unit up here is our welding machine. And this particular unit is a 3-in-1 welder, and it does MIG, TIG, and stick welding. Inside of it, we have a reel of wire. Now this wire is steel, but it's copper coated. And it is being driven by a motor to flow through this cable and come out in our welding gun at the very tip. And so when we pull the trigger, this reel will start to turn and the wire will advance out of the welding gun. On the rear, we have a highly pressurized cylinder of CO2 and argon. And this is a compressed gas, and it's a shielding gas. And its purpose is to prevent oxidation of the metal at high temperature, which is very common when you start heating metal up. Oxygen out of the air gets onto it very quickly. So, hang on here. Can you folks still hear me?
Yes.
Okay. My radio decided to go dead. That's fine. So, we have the CO2. We have some magnets for holding metal in position while we're welding. Those are very handy. We have an electric drill with a brush on it, and this comes in very handy for getting the oxide off of the metal. We have a clamp used for holding two pieces of metal together at an angle where we can weld them. Another very handy piece of gear. We have our handy dandy welding pliers. And these are important because they help cut off excess metal that's coming out of our tip. And they also help us grab pieces of hot metal. When you start welding on something, you generally create a lot of heat. On the other side of the cart, we've got a ground clamp, because in welding, you have to make a complete circuit. So that means we have to clamp a ground wire onto the piece of work that we're doing, or we can't get the electricity to flow from our welding tool into our metal. There's an arc that we're trying to create called plasma. In addition to that, we have another toy. It's pretty fundamental, gotta have it. This guy is called an angle grinder. And he's really important. We'll be using him tonight to knock off corrosion and dirt prior to doing our welding, because welding with dirty metal is a bad story. You don't get a good weld and it can break loose on you, and depending upon what the weld is holding together, the results can be disastrous. So if you want good, strong welds, you start out with good, clean metal. Okay, we also have some cables, and we have some fireproof gloves. We'll also be introducing you to a couple of other pieces of the uniform, which are the welding face shield and the welding jacket. And I have this handy little guy. This is for my knees, because you're doing a lot of welding on concrete floors. You're going to wind up with sore knees if you have to spend a lot of time. So I like a cushy something or other to put my knees on if I'm down on the floor for any length of time, and so I keep that on the cart. Then I have a pair of tongs, and these tongs are to grab a piece of metal that I've been welding on and quench it in a 5-gallon bucket. And we'll be doing that tonight. It's very important to have a way to quench your hot metal. Okay, so these are the basic pieces.
Carl, you said this is called MIG welding. Is that an acronym for something?
This is, yeah, MIG. I don't remember the name of the acronym right now, but there's MIG, TIG, stick, and torch, and we do all 4. This machine will do 3 of them, and then we have an oxyacetylene rig to do the 4th one. So, all right, I'm going to take this and maneuver it out to the welding area, and then I'm going to have you come out, and we'll have a volunteer suit up and join me at the welding bench. But we'll do a demonstration first, so you kind of get an idea of what's going to happen. So you can watch the screen there.
This will be the principle of see one, do one, teach one. So first he'll demonstrate so you see it, then you'll do it, and then you'll have the opportunity to teach somebody else sometime.
It'll take me a couple minutes to get set up here, and I'll talk you through it as I'm going along. The first thing I'm going to do is take this extension cord and we're going to plug it into the wall. Next thing we're going to do is we're going to take this adapter plug and connect the welding unit to it. We'll be swapping it out with the angle grinder. So we've got our power to our welding unit now. We've also got our welding grinder. Now I'm going to dispense with the hood and get into a regular mask.
This cord is wrapped around your hose. Unplug. There.
Okay, you should all still be able to hear me now. And I'm going to now invite the other students to come out and couple up to the air pipes where they can stand and watch the affair. And we've got a couple of cameras. Okay. We have this one, and we have this one. So, Evan, why don't you go ahead and unplug and come on out here.
Right now on the screen you're showing the chem locker.
Hold on a second. Okay, what'd you say, Dave?
Right now on the screen we are looking at the chemical locker.
Oops, that doesn't help. Hang on. How's that look?
Yeah, that's right.
Okay. So Evan, come on out. Why don't you go ahead and plug into one of those air taps. Okay, handshake, come on out. Caleb, come on out. David, come on out.
Your camera angle is being blocked by the people in suits. Okay. Kind of follow the message here. We got a couple things we're going to do. The first thing we're going to do, I have some welding that I've done on a previous piece of metal. I'm going to pass this around, let you just take a look at it. I want you to look at the weld in the middle. There are two lines of welding in the middle. One is a bead weld. The other one is a not so good example, but it's the beginning of what's called laying dimes. Dimes like in 10-cent coins. Laying dimes is a welding terminology, and it's something you do with a MIG welder to create a wider weld or seam across two pieces of metal. Now, the first thing we want to do is we want to take the oxide off of this metal. There's a couple of ways we could do that. I could take a high-speed metal brush as you can see, it eventually gets down to the bottom, but it takes a while. That's not completely so good. So what we're going to do, we're going to take an angle grinder and go after it. And we're going to prep our metal. Now I'm going to take this piece of metal I've been working with, and you can see there's a high degree of oxide on it.
This is called an angle grinder because it actually comes at the metal at an angle. Okay, now I have a nice clean piece of metal here. I'm going to do two things to get it ready for welding. I'm going to clean off a space for the electrode. And I'll put that out here on the edge, and then I'm going to clamp the metal to the table.
It looked like some of those sparks were hitting you. Do they not hurt, or are you just super?
I can't hear. Who's talking?
I was.
What was the question again?
It looked like some of the sparks were hitting you. Did it hurt, or were
No, I don't
you
need
just
to feel
super?
them. From the angle grinder, you need to protect your eyes. That's a number one. But the sparks are very, very small pieces of metal, and in most cases not significant. However, from here it gets a little more exciting. We're going to turn on our acetylene. We'll plug in our welder. We'll take our grounding cable and clamp it onto the work. We'll take our torch end and we'll unroll it. And the reason for that is because inside of it is this welding wire that's moving. And you don't want a kink in this cable or it'll bend the wire. So it should be laying out nice and straight. Okay? Now, we're done with the angle grinder for right now. The next part of this we'll put on a welding jacket because we're definitely going to throw some sparks around now, and we definitely don't want to get some of this on us because it will hurt and burn.
Is that gas the acetylene or the CO2?
This is CO2. We're not doing acetylene welding.
Okay.
That involves a different kind of welding apparatus. This uses electricity to generate heat instead of acetylene gas, which is a fuel that generates heat. The next thing I grab is my Rocky Jones Space Ranger hat. This is very important. It's got to be pretty. Now there are some switches inside of this thing. This is an oxyacetylene igniter. Okay? And I can put my welding hat on, pull this down, and when I strike it, I should see that my lens goes dark. Now, I'm not going to try to wear both of these at the same time. That's a little overkill. We're just going to strike. Okay, we've got a problem. I know what's happening here. Bear with me. Okay. Got to get this on the outside. Or nobody's going to hear anything. Okay. I'm going to ask you to take this, not try to put it on, but just hold it up like this to your visor and look through it at the spark. I don't want you looking directly at the spark. Okay, this one, it has a tilt up, but it works approximately the same way. Okay? So when the spark lights up, you can come look at it, but I only want you looking at the spark through your shield, because it's too bright for your eyes. So my first weld is going to be about 30 seconds, and basically I'm just going to lay some metal down. I'm not trying to do anything special, but giving you an idea of what welding looks like in this degree. This will be interesting because I got rubber gloves inside of welding gloves. So this is an interesting combination. Somebody give me a time check. What are we on time?
8:30.
Okay. All right, here we go. Okay. So, the first thing you got to remember is right now that metal is hot. And you do not want to just reach out and grab it. So we have, I can slide through here. A bucket. And we have our welding tongs. We'll move our clamp off. We'll get a good bite on this piece of metal. And then I'll release my clamp. I'm going to get this on. Both ends. You can see the steam coming off of it. So you can kind of see a blue steel there. Now I'll take my brush . That don't work too good.
Carl, looking through these, I could see the spark, but nothing else. How do you see what you're welding?
Excuse me?
Looking through these, I could see the spark, but nothing else. How do you see what you're welding, that you're in the right place?
Okay, those are fixed at a specific restriction of light. They're probably too strong at a distance for you to see much. But the welding helmet has a dial, and it actually controls how dark the glass gets. So I can control how much or how bright my working material is and whether I can see the table around it. So I've got control in the welding helmet. You down, nanny, nanny, boo-boo. So here, you can see I started off with a pretty good weld and then I got crazy and I messed up down here. So I wasn't maintaining the nice flow that you see up here. But this is a weld, and it has actually gone all the way through the metal and is bonding this material out here to the metal inside the plate. So it's one piece of metal now. So we use this to stick two pieces of metal together. That's what you do with welding, is you stick pieces of metal together. So the objective is, if we're going to make a corner, then we have to find a place to weld it. So I'll show you some magic. Now that sets our piece up. And I got a second clamp. And as you can see, it brings those two together. So now I can see what I'm welding, and I can run a bead right down that area and make it stick. And I probably do it like that because that gives me a nice level surface to take my bead along. But for tonight's purposes, I think it's better for us to just do straight strip welding until we sort of get the hang of this. Now that you've seen it, I want to talk a little bit about what's happening. There's two things that are happening. When I pull this trigger, wire starts coming out of the gun. That wire goes down and it touches the metal surface. The moment it touches the metal surface, it explodes because of the electricity in the wire. And that explosion is continuous because we're constantly putting more and more wire into the explosion. So what it's like is we're having a short circuit, and we're keeping that short circuit happening continuously. That's the objective. So we're going to short this wire out against this metal constantly and try to keep that little ball of bright light heating the metal that's coming out of this gun until it becomes a puddle. And then we take that puddle and we just pull it along and make it go where we want to. The metal that's being applied to the plate is coming from the gun, so it's just a matter of pulling the trigger. Now there's two things you've got to keep track of. Number one, you're watching the puddle, and number two, you're trying to keep this welding gun from actually touching the metal, because then the gun will start welding. This is a bad thing. It'll weld that tip to the surface. Your wire will stop moving. Things will stick. We'll have to take pliers and chip and hammer and pound and try to get the welding gun off of the metal. So that's not a good thing. So you don't want to actually touch the gun to the metal. You want to hold this about a ½ inch away and let the metal alone strike the metal as you're going. Now, who wants to try this? Okay. You're going to take off your helmet. Go ahead, disconnect your microphone first.
Sorry, say that again?
Just disconnect your mic. Okay, and put it in the box. Okay, and then just take your hood straight off. Now, I bought this jacket for students, and I know you've got bigger shoulders than I do. So this is going to be a trick. Okay. Okay. Now, so watch what happens when I pull the trigger. See how that works? So sit down to the bench. Put on the helmet. Is it fairly tight? Yes. Okay, can you see the plate? Okay. So back up a little bit.
Carl, do you want the other helmet?
Yeah, I do. That's a good idea. Thank you.
Safety first.
Okay. Now oh, you didn't put it on the wrong hand. Oh, shucks. Okay. Now, for the first time, I don't want you to try to hold an arc as long as I did. All I want you to do is create a puddle. So you're going to point this down here at the middle, about a ½ inch away. You're going to pull the trigger until you get an arc, and you're going to try to get a puddle of metal there, and then pull back. Once you've got a puddle that you can see. Okay, so 3 to 5 seconds, a while, but don't. Okay, so pull. Yeah, go ahead. Pull the trigger and go. Good, good. Okay. Yeah. Now go ahead and make another puddle next to it. Yeah. Okay. Okay, make a third puddle. Well, this time I want you to actually, let's go between the two, make a puddle, and then try to do what I did. Make it walk along. Oh, you got long, okay. Whoa! Drop in the bucket. Okay, so this time Right down the center here, I want you to make a line that looks like mine. Hold on, let me cut your this metal off. Okay. Okay, pull back. Pull back. No, you're done. We're done. Okay, let's let things cool down.
It's hard to tell like how far away this is.
It is. Take a look at how far you were.
Yeah.
So a couple inches. We'll take a look at what that does after we get it quenched. So I need you to roll back. Because right now this puppy is hot. Okay. So if you get up there close, you can get a look at it. You guys can come on into your link to your hose and look at his work. You can see you've definitely created a series of puddles, but they aren't overlapping or laying on each other. That's where you want to get to. What time have we got?
Quarter till.
Okay.